Arthur.
Yep. Say again.
I will have to share screen.
Yeah. Okay. So you go first.
Now.
Are we live? Okay. Hi. Welcome to the lecture on kernel methods. This is the first of the 2 lectures. So we are very happy to have Arthur Gretton to give a lecture on this topic. Arthur is a professor at the Gatsby Computational Neuroscience Unit at University College London in the UK. He received his undergraduate and master's degrees in physics and systems engineering from the Australian National University, or ANU, and a PhD from the University of Cambridge in the UK. He worked as a senior researcher at the Max Planck Institute for Biological Cybernetics, also in Tübingen. And also he worked at the machine learning department at Carnegie Mellon University. So his recent research interests in machine learning include the design and training of generative models, both implicit models like GANs and explicit models like high-dimensional or infinite-dimensional exponential family models. His other interests include non-parametric hypothesis testing, survival analysis, causality, and kernel methods. So you probably have heard of the MMD, or maximum mean discrepancy. So Arthur Gretton is the key person behind the MMD. So without further ado, please virtually welcome Arthur Gretton. And so Arthur, please, the stage is yours.
All right. So thank you. And I'm very happy to be virtually in Tübingen. Generally, when I give talks, I really like lots and lots of questions and interruptions. So it's a little bit more challenging, of course, to do that in a virtual environment, but I'm going to pause regularly and ask for lots of questions. So, please don't be shy to let everyone know or let the panelists know when there's anything not clear, and I'll do my best to clarify. Okay. So even though I've got 2 talk slots, my lectures go in 3 parts. That's a sort of content-based demarcation. So there'll be a little bit of slide switching somewhere along. Okay. So I'm going to start with a couple of motivating examples. So the first motivating example is that, let's say that life has given us 2 collections of objects. Drawn from 2 different distributions. So in this case, I have a collection of dogs and a collection of fish. And I've got a P, a distribution that generates dogs, and Q, a distribution that generates fish. Now, in practice, I see perhaps only samples of these dogs and these fish. And on the basis of these samples, I want to know if P and Q are different. Okay, so this is a little bit of a visual key to this problem, but let's make it a bit more practical. So, recently, Ben Recht's group has tried to reproduce the CIFAR data set, like a bunch of little images from different objects around the world. And they made a new data set, CIFAR 10.1, and there's an earlier version of the same data set, CIFAR 10. And a question might be, is CIFAR 10.1 from the same distribution as CIFAR 10? So it's supposed to be from the same distribution. Like, they made a lot of effort to reproduce all of the mechanisms whereby CIFAR 10 was generated. And so then you might, you have your collection CIFAR 10, you have your collection CIFAR 10.1, and you might want to test whether in fact they are from the same distribution, or whether there is some subtle difference in the distributions of these little images that hasn't yet been discovered. Okay, so this is a practical real world setting where comparing sets of objects is an important thing to do. Okay, one can also compare sets of objects as a way to train a generative model. So if you have a measure of how far apart 2 sets of objects are, you could use that as a training signal for a model. So a famous instance of this is in training generative adversarial networks. So a generative adversarial network takes as a reference a collection of objects, like a collection of images, a collection of text, a collection of sounds, and then tries to create a distribution of objects which matches that training set, okay? So for example, if I give again a set of bedroom pictures, what I want it to do is to produce a set of bedroom pictures from the same distribution. But obviously not just a trivial thing of just copying the pictures across, but I want to create new bedrooms from the same distribution as the original one. So here, if I have a measure of similarity between one set of images and another set, I could actually optimize that. I could improve my GAN so that these distributions match. Okay, so that's another task I might do. So, this is going to be the theme of my talks, both today and tomorrow. I'm going to be exploring ways of taking sets of objects and comparing them. And the tool that I'm going to be using this is kernel methods. So that's, I'm going to sort of be motivating my teaching you guys kernel methods so that, this is one of the tasks you'll be able to accomplish. I also want to flag a couple of problems that you can solve using the techniques that I'll describe, but which I won't go into. I'm flagging these techniques so that if you encounter problems along these lines later on, you'll be able to sort of find the literature you need to solve them. So one setting is comparing samples and a model, okay? So here's an example. Let's say that I want to model crimes in Chicago. So here is a map of the city of Chicago, and each little blue dot is a crime, okay? And let's say that I've got a red model. I'm a statistician. I've made a model of the crimes in Chicago, and I want to know if it's a good fit for the data. So let's say that I'm not a very good statistician, and this is my model. I've just done a mixture of two Gaussians. Now, it's kind of obvious, to me visually that this isn't a good model because it's putting crimes where there aren't any. But maybe I want an automated and informative way of comparing my model to my data. So this is a little bit different to the setting before. So before I had a set of points from P and a set of points from Q. Here I have a set of points from P, but I have a model from Q. It's a slightly different problem, and I want to know where my model doesn't match my data. So here is another setting, which I think is an interesting variant. And this is finding dependence. So dependence is a kind of interesting task. Here you've got, let's say, a picture, and you've got some text, and you want to know if the picture and the text are related. So to give an example here, the picture is a picture of an animal, like a dog or a cat. And then the caption is a caption that accompanies that text. So the first is a hound dog, and then it's like the caption is a large animal who slings slobber and exudes a distinctive houndy odor. So, what's challenging about this task is that mapping from caption to image might be actually difficult, okay? So unless I know quite a lot about dogs, I might not be able to know that the Y maps to that picture, to the X. But I might, I might want to detect the dependence between the images and the caption without having to learn the harder problem of regression, of regressing from caption to image. And the tools that I'm going to describe can also be used in this task. So this is another of these domains where we can use these tools, but I probably won't get to that in the course. But just so you know, the tool is available, and if you want to use it, you can. All right. So I'm going to sort of go from general sort of fundamentals to specifics in particular applications. So I'm going to start with the most, I think, abstract and mathematical part of the course, because it's early in the course, and that's when everyone's most focused. So I can give the hardest material now, and then I will sort of go on to the examples that I described as I move into the slides. So, but the reason I'm teaching these abstract tools is for the purpose of later on being able to use these in the tasks that I've just described. So that's going to motivate the tools that we learn. Okay, so as I said, I'm going to use kernel methods to solve all of the tasks that I've described. And to be able to do that, I need to describe to you what kernel methods are. The key object in kernel methods is something called a reproducing kernel Hilbert space. So I'm going to go through each of the words in that title. So first of all, what is a Hilbert space? So that'll just be 2 slides. Then what is a kernel? I'll give some examples. And then finally, what's this thing called a reproducing property? Now, the key thing that I need you to take from these slides is that kernel methods are a way of enforcing smoothness. And that's the important property that we're going to be using in the subsequent slides. And so if nothing else, this is the property you should take home. All right. So then, following that, I'm going to actually start this today. I'm going to talk about the maximum mean discrepancy. This is a way of looking at differences in sets of objects. I'll describe it as two different ways. Difference in feature means as an integral probability metric. The latter, I'll describe what that is. And then I'll talk about statistical testing. And then finally, I'll talk about how to train GANs. So the GAN training is probably going to be in tomorrow's lecture. Okay, reproducing kernel Hilbert spaces. So if you've encountered RKHS in prior machine learning course, this is probably the way that you've encountered it, or this is one of the main ways in which you've encountered it. So let's say that I have a classification problem in a low-dimensional space. I want to classify blue from red. Now, there is no simple decision boundary that separates blue from red, okay? So if I want to make, for instance, a linear decision boundary, like a straight line, there is no straight line that separates blue from red. But let's say that I map my points to a higher dimensional feature space. So here I take my point, and I map it, in this case, to 3 dimensions. So this is what I have on the right here, where I've added a third coordinate, which is the product of the first 2 coordinates. And you can see that that pushes the blue points above the plane. It pushes the red points below the plane. And then I can separate my blue from my red using a linear boundary, which is basically the XY plane. Okay. So in this case, my feature space is 3-dimensional, but in practice, I might even make it infinite dimensional. And this is a sort of classic way of understanding kernel methods. Like kernel methods take a low-dimensional problem, they put it into higher dimensions to make that problem easier. And a key property is that this space can be infinite dimensional. And so unlike, for example, a neural net, I'm able to use infinite dimensions. Just as a sort of point of relevance here, this is one of the ways in which I think kernels are quite informative about modern neural nets, because one way that one can model neural nets as they become infinite dimensional is using an appropriate kernel. So neural tangent kernel is a great example of that. There's another way to think about infinite dimensional spaces, which I think is also very informative. And this is as a way of describing the smoothness of the functions that you have. So for example, let's say I'm doing regression. I'm doing a very simple regression problem, and I've got a set of blue points and I want to fit a line through them, okay? Now, visually, I can see that maybe the line on the left is too smooth. The line in the middle is, the line in the middle is too rough. And then the line on the right-hand side is about right. It's not too smooth, it's not too rough. Now, each of these lines are basically functions in a space of infinitely many features where I've prioritized smooth features and I've penalized rough features. And this is another way in which kernel methods can be understood. And I think, for the purposes of the rest of this talk, this second way is actually in many ways the most informative one. And so I'm really going to emphasize this in the theory section so that we can use this intuition later on as we get to some examples. All right. So reproducing kernel Hilbert space. So let's start with the final bit of that phrase, which is Hilbert space. So to the, I think, distress of mathematicians in the audience, I'm not going to spend too much time on that. I'm just going to give a very elementary introduction. First of all, I think we all know what an inner product is, okay? So if I have a vector space, like a space of objects, for instance, vectors in RD, then I can take the dot product. And the dot product has some properties that we know quite well. So if I take the dot product of a weighted sum of 2 vectors, f1 and f2, with a vector g, that's the sum of the dot products with weights alpha1 and alpha2. Dot product of f and g is equal to the dot product of g and f. And finally, the dot product of f with itself is greater than or equal to 0. And that arises because the dot product of f with itself is just the squared length of the vector f, okay? So, if f and g are just vectors in RD, then this is just the standard vector dot product. This can also be defined, though, if f and g are functions or, vectors of infinite length. So for the purposes of these lectures, this is all we need to know about Hilbert spaces. So Hilbert spaces are spaces with dot products, and they have additional formal properties, which we're not going to talk about in this lecture, which is that they contain certain limits. Okay. So, but for our purposes, Hilbert spaces are spaces with dot products. Okay. Now, what is a kernel? A kernel is actually a very simple thing. If I take an object in a space X, calligraphic X, if I define features, phi, of those objects, then a kernel is simply the dot product between features. I'm in a Hilbert space, so I have a dot product. I define features of my objects. A kernel is a dot product of features. Done. Okay. So, what is X? X can be anything. X can be a picture. X can be a book. X can be a sound. X can be whatever you like. Okay. As long as I can define a feature of that X, and I can take the dot product between those features, then I have a kernel. So if I have finitely many features, then I might be able to express these features explicitly and get a kernel. If I have infinitely many features, then I can only manipulate these features via the dot product because I can't write down an infinite vector. So, depending on whether I have finite or infinitely many features, I may or may not have an explicit form for my phis. Okay. Just as a sort of additional formal point, you can actually, and rather trivially, get more than one feature with the same dot product. So I've given an example here where the feature of X is just X and X is a scalar. I will get the same dot product if I make this two-dimensional vector and take the dot product. So this is just to warn you that even though the kernel is unique, the features that define it might not be. And there are sort of trivial ways to construct these. Okay, so this is a pretty straightforward thing. Like, what is a kernel? Kernel is a dot product between features. What is a Hilbert space? It's a space with a dot product. So now, how do we construct kernels? So one way to construct a kernel, like a kernel, you can think of as a measure of similarity between objects. So it's a dot product between features. If the dot product is large, then these features are probably well aligned and the objects are similar. If the dot product is small, then these features are close to being orthogonal. So the dot product is different. Okay. So let's say that you have two kernels, K1 and K2. And these are different measures of similarity on my objects. Okay. Then I specify to you that the sum of two kernels is a valid kernel. Okay. So let's say I have one kernel on shapes and one kernel on color. If I take the sum, that's a valid kernel as well. I'm going to prove that to you later, but for now, just take my word for it. So, this is one way of combining kernels on different views of objects and getting a more complicated kernel. Okay. Another way of combining two kernels is using products. Okay, so if I have two kernels, the product of the kernels is a kernel. And this one actually has a very simple proof. So I'm going to show you how this is proved right away. Okay, on the previous slide, I talked about combining kernels on shapes and kernels on colors. So let's say that I have a feature map here, phi1, which is a feature map that describes shape. So let's say the objects in my world have one of two shapes. It has either a square or a triangle. Okay, so that means if I have phi1 and the input is a square, it will have a 1 on the top where the square comes in and a 0 in the triangle slot. Okay, and then the kernel is a dot product of features. So the dot product of a square and a triangle is 0. Dot product of a square and a square is going to be 1. Okay, now let's say that I have a second feature space, which is my feature space on colors. All right, so feature of blue gives me 0, 1, 1 in the blue slot, 0 in the red slot, and kernel between red and red is 1. Now let's define a feature space on colored shapes. Okay, so this capital phi of X has indicators of every possible permutation of color and shape. Do I have a red square or a red triangle, blue square or blue triangle? All right, and this matrix can be very trivially written as an outer product of one feature vector, the feature vector of color, and a second feature vector of shape. Okay, so phi2, which is my color feature vector, phi1 transpose, my shape feature vector. Okay, so I can write it either as a big long vector or I can write it as a matrix, but I'm going to write it as a matrix for reasons that will become clear. Okay, so what is my kernel between two objects? okay, which have both color and shape. It's going to be the sum of the features across colors and shapes, okay? So it's going to be basically the sum across every combination of features and colors of object X, and producted with the sum, with the features and colors of object X prime. Now I can write this as basically a trace of phi1, phi2 transpose of X and phi2, phi1 transpose of X prime, okay? So let's look at the second term, phi2, phi1 transpose. Well, this is the matrix form of my color shaped features, okay? And this trace of phi1, phi2 transpose, phi2, phi1 transpose, this is just the dot product of the features of X and the features of X prime when these are matrices, okay? Now let's look at phi2 transpose phi2. Well, this is just the kernel between the colors. That's a scalar, so I take it outside and I put it here. Then I've got, by the cyclic property of the trace of phi1 transpose phi1, which is the kernel between my shapes, okay? So I've got the product of the kernel of my shapes and the kernel of my colors, and that's the kernel of my objects. So let's now zoom out a bit. What we've noticed is that if I have this kernel here, this is basically an AND kernel. If my colors and my shapes agree, it's 1. If there's any disagreement whatsoever, it's 0, okay? So this product kernel is like an AND operation. If I've got every feature agreeing, then my kernel is large. But if I've got any of my features disagreeing, then my kernel is small. So this is sort of conceptually what you should think when you're taking a product of kernels. And you can think of a sum kernel, abstractly speaking, as an OR operation. If in no mode are the objects similar, then my kernel is going to be 0. But if the objects are similar in any way, in shape or in color, then my kernel is going to be away from 0. Okay, so this is a way of taking kernels on features and combining them. So sums of kernels are kernels, products of kernels are kernels. All right. Now, since sums of kernels are kernels and products of kernels are kernels, I can take polynomials, which are basically, an expansion of sums of products of kernels, and that's a valid kernel. So this takes a small amount of algebra, but this is pretty straightforward. So this already gives you a big family of kernels. All right. So earlier on, I emphasized that the power of kernels arises when you start thinking about not finitely many features of my objects, but infinitely many features of my objects. So if I have infinitely many features, the only way in which I can manipulate these features is by using their dot products, because I can't write them all down. Okay, so let's now explore what happens when we have infinitely many features. Actually, before I do that, are there questions so far? Has anyone raised their hand yet?
Not yet.
Not yet. Okay, good. Okay, so the moment you start getting infinitely many features, there's a lot of tricky things that can trip you up. Okay, so one of the things you need to make sure of is, if I've got infinitely many features, do I just get a kernel which is infinity everywhere? That's a possible risk, right? And it's not very interesting. If my kernel is infinity, then I'm kind of like not, it's not a very informative or interesting kernel. Okay, so I need to first of all check that this kind of boring thing is not going to happen. So for this, I'm going to introduce a little bit of notation, which is the square summable sequences. So this is an infinite sequence. Okay, so it's a sequence with infinitely many numbers in it, but the sum of the squared entries of that sequence is still finite. So these A's, A sub L is getting smaller and smaller and smaller fast enough that when I take the sum of the squared A, I'm still getting something which isn't infinity. Okay, where is this relevant? Well, what if my features of my X are square summable? So I've got infinitely many features of my X, but nonetheless, if I take the sum of the squared features, still I have something finite. In this case, my kernel is not going to be infinity. Okay, so my kernel is still going to be finite, and it's still going to be an interesting thing for me to think about. So the proof of this is very short. If I take the dot product between my features of X and my features of X prime, and I take its absolute value, then by Cauchy-Schwarz, it's upper bounded by the norm of phi of x, so the square root of sum of squared features of x, and the norm of phi of x prime, square root of sum of squared features of x prime. And so that means that if both of these are bounded, then my kernel is bounded. Okay, and it's not going to be infinity, and everything is nice. Okay, so this is a little pitfall which we have to worry about when we've got infinitely many features. All right, let's look at an example of a kernel with infinitely many features. So this is the running example for this talk because it's going to come up again and again, and it comes up all the time when we're looking at kernel methods. So this is the famous exponentiated quadratic kernel, or Gaussian kernel. So the kernel between x and x prime, I just take x minus x prime, I take its squared norm, divide by some width, takes a negative sign, exponentiate it, and that's a kernel. Now, I'm going to specify that that kernel can be written as an infinite dot product of features. Okay, where here is the construction of these features, it's square root of lambda L times these ELXs. So where do these lambdas and E's come from? The lambda and E's come from solving this rather complicated eigenvalue problem. Okay, so basically, I have my kernel here. I find the eigenfunctions of that kernel and eigenvalues. Then I expand the kernel in terms of these eigenfunctions and eigenvalues, and I get this expression here. Okay, so I'm not going to prove this for this talk, but I'll just illustrate this. And it's interesting to sort of see because you're using this kernel all the time. But when you're using it, these are the features that you're using. So let's look at what these features actually look like. So these lambdas are decaying polynomially. I've got b to the L, where b is less than 1. And these E's are Hermite polynomials with this Gaussian envelope. So what these look like as L goes up is that they get more and more wiggly. So here's like E1, E2, and E3. So as we go up, the features get more and more wiggly, and their amplitude gets smaller and smaller. Amplitude has to get smaller and smaller because we need these things to be squared summable, these features to be squared summable. All right, so this is the exponentiated quadratic kernel, and these are the features, the infinitely many features whose dot product define this kernel. Now, as I said, I'm not going to show you how to construct these features, but at the end of these particular slides, I am going to, we're going to construct together an infinite feature space right from scratch, and you're going to see how to construct these guys in practice for some example. All right. So let's say that I am given a function of 2 arguments, k, okay? And I want to know if that's a valid kernel. Is it really a dot product of features? So let's say somebody gave me this function here and said, is this a valid kernel? So one way to answer that question is to find a valid feature map, okay? And if you can define a valid feature map, then we know that it's a kernel. But as you might guess from the rather complicated expressions in this slide, sometimes finding a valid feature map is not so easy. And besides, as we saw earlier, rather trivially, the feature map isn't unique. But there is a property that all kernels have to have, which is the property of positive definiteness. And it can often happen that checking this property is sufficient to show that a kernel is a valid kernel, or a function of 2 arguments is a valid kernel. All right, so let's look at that. What is positive definiteness? So a function of 2 arguments is positive definite if for a set of scalars, a1 through an, and for any n greater than or equal to 1, so a1 through a10 or a1 through a20 or so on and so on, and for a set of objects, x1 through xn, okay, this sum here, a1, ai, aj, kxi, xj, summed over I and j, is always greater than or equal to 0. So this is the property of positive definiteness. And basically, a kernel is valid, it's a dot product between features, when this property holds. And it's an if and only if. So if this property holds, then my kernel is valid. Okay, and if my kernel is a dot product of features, then this property holds, goes in both directions. So this property looks a little bit abstract, but actually, when you think about it a little bit more, it's actually quite obvious why this is true. Okay, so let's do the proof. It's a very short proof. Okay, here is the sum from the previous slide, sum over I, sum over j, ai, aj, kxi, xj. So this is this expression from the previous slide. Now, remember that my kernel, let's say that I'm starting with the fact that my kernel is a dot product of features, okay? So k of xi and xj is the dot product between features of xi and features of xj, okay? So here is my feature of xi and my feature of xj. And remember, by the linearity property, I can take scalars inside my dot product. So I have a scalar outside the dot product here. I've got a scalar inside the dot product here. Scalar outside dot product, scalar inside dot product. Now, what I've noticed about this double sum here, I can also take the sums inside the dot product. And I see here that I've got the dot product of ai phi xi summed over I with itself. Now, the dot product of something with itself is the squared length of that object, right? So here's the squared norm of this vector here. And the length of something is always non-negative. So this is greater than or equal to 0. So you can see now, why positive definiteness is such a necessary and essential property when a kernel is a dot product between features. Because if a kernel is a dot product between features, this is just the same as saying that the norm of a vector in my feature space is greater than or equal to 0, which is going to be true for any Hilbert space. So this property is in a sense like a very intuitive and obvious property for feature spaces. But as I say, it's an if and only if. So if I have a positive definite kernel, then there must exist a feature space, even if it's really hard to find, such that the kernel is a dot product between those features. And that's the Morat-Ancien theorem. Now, some slides ago, I claimed that a sum of two kernels is a kernel. And I said that I wasn't going to prove it yet. So now I'm going to prove it. And the proof is super short because I've introduced this property of positive definiteness. And because of positive definiteness, I have a sum here. I break that sum into two. I know that both of these sums, this one and this one, are positive, and so their sum must be positive. So this is actually a very easy proof that the sum of two kernels is a valid kernel. But without positive definiteness, I've seen proofs that try to do this without using positive definiteness, and you can, but it's a real pain. So this is a short proof. Okay, are there questions about now so far? Yeah, good. Excellent. That means it's very clear. Okay, so I've defined kernels as dot products of features, and that's fine. But in machine learning, we need to make predictions, right? I have my features of my objects, but I need functions of those features. So maybe I'm doing regression, maybe I'm doing classification. So it's not enough to just say I've got these infinite features. I need to do something useful with them. And to do anything useful with my features, I need to define functions of them. And you should already be a little bit worried, because if I'm saying I've got functions of infinitely many features, well, how am I going to code that in my computer, right? So this is what the next part is about. Okay, so let's first introduce a notation when I've got finitely many features. So remember, I started the talk with this very simple feature dictionary where I had my first coordinate, my second coordinate, and my product of my two coordinates. Here is a function of that feature, okay? So I've got, well, it's a linear function, so I've got a scalar f1 times my first feature, scalar f2 times my second feature, scalar f3 times my third feature. I'm going to write f dot as this vector of coefficients, okay? Or sometimes I'm just going to write it as f, okay? So when I write f dot or f, what I mean is this vector of coefficients. And this is, in a way, this is how I express my function. It's the coefficients that define it. The dimension of f dot is the same as the dimension of my feature space. So here I've got 3 features, so f dot has 3 dimensions. When I write f of x, that means I've taken my function and I've evaluated it at a point x, all right? So in this case, when I evaluate my function at a point x, I get out a real number. So, I've just taken my f, I've taken the dot product with my features of x, and, I'm going to be able to write it like this. So f dot, which is the vector of coefficients, and then features of x. And H is the space of features. All right, so f at x is an inner product in my feature space. And then the space calligraphic H is a space mapping from my initial X, which is a 2-dimensional space, to R. But I take my X, I map it into a 3-dimensional feature space. I take the dot product with these coefficients F dot, and then I get my function out. So that's our notation. All right. Now, I might also want to define a function of infinitely many features, and I'm going to use exactly the same notation for that. So here is my f of x, dot product of f and features of x, but now I've got infinitely many features, phi1, phi2, phi3, so I've got this infinite vector of coefficients. I've got this infinite dictionary of features, so these are the features we saw already with the exponentiated quadratic kernel, and then that's going to define my function. Okay. And remember that my kernel is now an infinite sum of features of x and features of x prime. Okay, now I'm going to occasionally write the norm of f, and that's exactly what you think it is, which is the sum of the squared coefficients. Okay, if I've got f squared. All right. So it's a little bit of a pain to write down infinitely many features. So I want to find a way of expressing a function that doesn't require me to write infinitely many coefficients. So this is what we're going to do on this slide. So let's say that I've got a function here, which is a sum of infinitely many features. Okay. But now let's say that my coefficients f can be expressed as a weighted sum with weights alpha I of features of some points xi. Okay. So I've got m points, m here in my sum. And I take a sum of alpha I, m of these alpha i's, times features of m xi's. Now, each of these xi's I've got an infinite feature dictionary from, but there's only m of these xi points. Okay. Then my FL is going to be this weighted sum. So now let's substitute that. Okay, so I've got this I equals 1 to m, sum over alpha I, feature xi, dot producted with x. What's interesting now is that I know that the dot product of my feature of xi and my feature of x is my kernel between xi and x. Okay, so here is my sum of my kernels between xi and x. So now I have expressed my function of infinitely many features as a sum over just m points. Okay, alpha I, there's m of these weights, and I've written my kernel between xi and x. So here on the right, I've done an illustration of this. You can see these red bumps. These are my kernels, and they're centered at these points xi, and I've given each of these red bumps a weight alpha I. Okay, so these are my kernel functions. So, not all functions in my infinite feature space can be expressed as sums of m kernels, but some functions can. So the question then becomes, does my learning algorithm output a function of this form here? If it does, then I can express my function of infinitely many features. So that's restricting in a sense the class of algorithms I can consider. But if I use such algorithms, then I can express a function of infinitely many features using finitely many coefficients. Are there questions about that? Okay, that's good. So in a sense, like this is the power of kernel methods. Like I'm able to write a function of infinitely many features. As long as my algorithm outputs something that looks like this, then I have the power of infinite feature dictionaries. And this is very valuable. Okay, here's a fun subtlety. The feature map itself is a function, which seems a bit crazy, but let's see why that is. Okay. Here is from the previous page. My function of x, I've expressed it as a sum of m coefficients times my kernels between xi and x. Okay, this is from the previous slide, so you've seen that already. Now, what if I take a really simple function? What if I take a function where there's only a single term in my sum and my alpha is 1? It's a function, it's valid. Okay. Then here is my function. It's alpha is 1 and there's no sum, so k, x1 and x. So I'm going to sort of write this as a function of red x, which I'm going to express here as k x1 dot. Now this notation, just to be absolutely clear, remember that earlier when I wrote a function, I wrote f of dot, right, to indicate that I was expressing this as my vector of coefficients. This function here is a function indexed by x1 with a dot. So think of that as a kernel. My function is just my kernel centered at x1, but it's a function. But then you might look at that and say, but why that ordering? Why not write it as k of red x and phi of blue x1? And you're absolutely right. So k of red x is also a function. And the higher level picture of this is that my feature map is a very simple function. So the simplest function I can get in my space is the kernel centered at some x. That's a valid function. And therefore, we can write without ambiguity, k of xy is k of dot x and k of dot y. So k of dot x is a function, it's a kernel centered at x. K of dot y is a function, it's a kernel centered at y. So this seems almost like semantics, right? That I'm saying that my kernel, my dot product of my kernels is a kernel. But this is, I think, a quite fundamental property of reproducing kernel Hilbert spaces. And later on, when we construct an RKHS from scratch and we derive our feature spaces from scratch, you're going to see why that property is more interesting than it looks at first. All right. So now we get to the very final sentence in our reproducing kernel Hilbert space, which is the reproducing property. And from what we've described, it's a little bit of an anticlimax, I would say. So the first thing is like the dot product of f and k dot x, which is my features of x, is just f of x. That's true. And the dot product between features of x and features of x prime is my kernel between x and x prime. So this seems like a very trivial thing. And from our presentation so far, it is. And as we move on, it might become a little more surprising. Or by the end of these slides, it might become a little more surprising. But for now, this should be like really, really super obvious. Okay, are there questions so far? Okay.
I guess it's too clear.
Yep. So now, it seems like these properties, from what I've described, are very simple properties to understand. But now I'm going to get to sort of the meat of this first lecture, which is understanding why reproducing kernel Hilbert spaces enforce smoothness. And for this, we're going to be constructing a reproducing kernel Hilbert space from scratch, and we're going to be deriving the properties on this slide. And when we do that, we're going to sort of understand why these properties are a little bit more complicated than they first seem. And in the process, we'll understand why reproducing kernel Hilbert spaces allow us to get smooth functions. Okay, so this is the point at which I'm going to experiment with Zoom's functionality. So could audience members raise their Zoom hands, so to speak, if they are familiar with Fourier methods, or Fourier series, Fourier transforms, Fourier theory generally, just so I have a sense of what fraction of the audience has this mathematics. And Mijung, can you tell me roughly what fraction of people raise their Zoom hands?
27. 27
20.
of 92. Oh, 30.
Okay.
30. Okay. 28.
More, yeah.
Okay.
This is also my way of seeing like who's like drinking coffee and watching Netflix, and no, of course nobody. Everyone's. Okay, so I will say around a third of people. So don't worry, like this is completely self-contained, but I wanted to make sure that I wasn't telling people stuff that was super obvious. Okay, so as I say, like the lectures are entirely self-contained, so you don't need to know Fourier theory to understand what I'm going to say. But if you already know a little bit about it, it will help you to understand. Okay, I'm just going to, yep. Okay, so I'm going to define very, very simple functions. These are functions on the interval minus pi pi with periodic boundaries. So they're not only are they functions in one dimension, but they're functions on a small interval in one dimension. So this is like, functions that no one cares about in real life, but they're very useful because the math is going to become simple. Now I'm going to express functions on this interval using a representation, which is a Fourier series representation. Okay, so this is going to be an infinite sum of coefficients f hat times these things here, e to the square root of -1, coefficient L times x. Now this exponential here, this complex exponential, I'm going to break down into a sum of cosine and square root of -1 times sine. Now, this means that I have a function which can be complex valued, but all of the functions that I care about are going to be real valued. So the square root of -1 is just because we're using Fourier theory here. But you can see that you're sort of assembling a function using functions that become less and less smooth. So these cosines, as L increases, are going to get more and more wiggly. Okay, now this basis, this e to the ILX, is an orthonormal basis. What does that mean? It means that if I take the dot product of e to the ILX and e to the IMX, it's going to be 1 if L and M agree, and it's going to be 0 if L and M don't. So each of these pairs of functions is orthogonal to the other. I'm also using this bar notation. So the bar notation just means that I put a minus sign in front of the square root of -1 here. And I need to do that if I'm doing a dot product in a complex domain. Okay, so in real valued, I wouldn't have to worry about this bar, but if I take dot products of complex numbers, then the second item in my dot product has to get the bar on top of it. Okay, another way to understand this bar is that I just put a minus sign here before the complex part. So I put a minus sign here before the square root of -1 sine LX. So I'm going to remind people of that as we go along, so you don't forget what the bar notation means. Okay, so that was a little bit abstract. So let's look at our real function. Okay, we're going to look at the top hat function, which is going to be 1 on an interval where x is smaller than capital T, and 0 when we're outside of that interval. And just to give you a key to what's going to happen in the next couple of slides, the coefficients that define this thing are going to be sine of LT on L pi, and the function I'm going to express as the sum here, okay? Sum over L equals 0 to infinity of 2 times f times cosine. Now, you might already wonder what's going on, right? Because I've expressed this f as a sum from 0 to infinity, rather than a sum from -infinity to infinity, as I did up here. And I've got a factor of 2. So what happened? Okay, so what happened is that these f's are symmetric. Okay, so these f's are symmetric, and sine is anti-symmetric, whereas cosine is symmetric. So that means that when I take this sum, the cosine terms basically double up. So f of -L is equal to f of L. And so I get 2 times cosine, etc. But then these anti-symmetric functions cancel. And so they go away. And that's why I've got this sum only from 0. And I've got a factor of 2 here. So let's look at what this looks like. OK, so on the left hand of this slide, I've got my top hat function in red. And this is the function that I'm trying to express in terms of the simple basis function, these cosines and sines, or in this case, just the cosines. Okay, f of x is a top hat. And you can sort of see the interval minus t to t where this function is not 0. Okay, now L equals 0 is a constant offset, so I've added that. And now I've got my first basis function, this cosine with L equals 1, very, very slow moving function. And I'm approximating my top hat so far with just one of the terms in this sum. Okay, L equals, from 0 to 1 rather than 0 to infinity. And you can see that my approximation to that top hat isn't very good yet. Okay, now I'm going to add the second one, L equals 2. Well, funnily enough, L equals 2 actually has a coefficient of 0, so it doesn't even appear. Okay, L equals 3. This is this slightly more wiggly cosine. And it has a negative coefficient here. So f hat L is negative. And you can see that adding this third basis function means that my function is starting to look a little bit more like my top hat function. Okay, L equals 4. Well, that doesn't appear. And so on and so on. I can add more and more functions. And you can see that as I add more and more of these functions, they get more and more wiggly. Their amplitude gets smaller and smaller. And I'm getting something that gets closer and closer to my target function. So, as I add more and more coefficients in my infinite sum, I'm getting closer and closer to the target function that I'm after. So this is the mental image that you should have when you're understanding a Fourier series. I'm taking a function and I'm expressing it in a sum of functions that gets less and less smooth with coefficients that get smaller and smaller. Okay, so that's the top hat function. So now I'm going to use Fourier series to explicitly construct a feature space. So we're going to construct a feature space from scratch. And that's going to be sort of the rest of this slide deck. Let's say that we have a kernel, K, which is a function of the difference of its arguments. So this is the same as, for example, an exponentiated quadratic kernel. It's a function of the difference of the arguments. All right. Now, since the difference of the arguments is just a single number, I can find the Fourier series of this K. Okay. So here is my K, it's a function of the difference of the arguments. It's going to be an infinite sum of these Fourier coefficients times the exponential of square root minus 1 times L, the coefficient, times x minus y, the difference of the arguments. Now I'm going to split this exponential into the product of exponentials, e to the ilx and e to the minus ily. And, you know, what does this look like? Well, this thing here looks like a feature of x. This thing here looks like a feature of y. And we've just expressed our kernel as the dot product of features of x and features of y. So using Fourier series, we have now defined our kernel. We've basically used the Fourier series expansion as a way of constructing the feature space. So now let's look at an example. So here is a K of x minus y, and I've used rather horrible notation here. But what this looks like is a Gaussian kernel in this space minus pi pi. So a Gaussian normally is something that goes, you know, off to infinity, right? As x goes to infinity, it decays like a Gaussian. Because we're stuck on a periodic, because we're stuck on a compact domain minus pi pi, and we've imposed periodic boundaries, this is sort of like what a Gaussian looked like when it's stuck on minus pi pi and it has to keep repeating. And in particular, the coefficients k hat here, over here, they decay like a Gaussian. So the Jacobi theta kernel is like a Gaussian kernel for this compact domain. So let's construct it using exactly the same method that we used to construct our top hat function. So we've got our constant offset, L equals 0, and now we're taking just the first term in our infinite sum. Okay. The kernel is symmetric, so the sign terms in our Fourier series vanish again, just as before, and we only keep the cosines. So here is just the first cosine. We're approximating a Gaussian-looking function by a cosine function. Evidently, that's not a very good approximation. Let's add now a second cosine function, second basis function. Now it's getting a little bit closer, and you can see the coefficients that we've used. Now let's add a third one, this sinusoid that's oscillating 3 times, L equals 3. It's getting closer and closer and closer and closer. And you can see that basically the approximation is extremely good, which is not surprising because my coefficients are decaying fast. So you can see here that we have constructed our kernel as a dot product of features, and you know this has worked pretty well. All right. So the next challenge for us is to check the famous reproducing property. And this is where, you know, my foreshadowing from earlier now becomes relevant. So I said, okay, here is the reproducing property. It's something very trivial. It should be completely obvious. I'm now going to introduce the reproducing property using the Fourier notation. And it's going to tell us something very interesting about the RKHS. So actually, before I do that, I think this is maybe a good time to see if there's any questions about this Fourier series stuff.
Yes, yes, we have a question.
Excellent. I'm very happy to get questions. Tell me questions.
Maria, do you want to actually ask him, or should I just read? Okay, cool. What does it mean? Should I read? She said cool, but I don't know what it means. Okay, I will just read. Hey, Arthur, just to make sure, that means that a minus means that every kernel of form k x minus y has an associated feature map where the features are just Fourier basis functions, right?
Yep, that is exactly right. So basically, this k minus y, I could do this like I'm doing it here with a Jacobi theta kernel, which is like a Gaussian kernel. But you know, I could do this with another kernel as well. That would change these little k hats. The basis functions E wouldn't change. So these functions here would stay the same. ELX and ELY would stay the same. So in effect, what would change about my feature representation is that these k hats would change shape and would decay either slower or faster. Yeah.
Okay. Somebody else said, "Oh, that's Buchner's theorem," and oh yes. Okay.
Yep. So that is correct. So there is a theorem called Buchner's theorem, which tells us that any translation invariant kernel can be written as a Fourier transform of a finite non-negative measure. So what I'm showing you here is called Buchner's theorem. That's absolutely right. Yeah. Okay. And this theorem, by the way, applies even not on minus pi pi, but we don't like the minus pi pi one is a good one to work with because it gives us some nice simple expressions here. If I had a non-compact domain, I would have to use an integral rather than a sum, and then it becomes a little more complicated. Yeah.
Okay, that was the only question.
Only question. Okay, actually, I'm going to therefore ask a challenge. Actually, no, I won't ask the challenge yet. Okay, I'm going to ask the challenge later. Okay. Let's now, I've now said, okay, here's my feature space for my kernel. I've introduced the Fourier transform notation, but now I need to go and construct I need to now sort of verify my famous reproducing property. And in verifying the reproducing property, we're going to sort of see that it's a little bit more subtle than it at first appeared when we introduced it earlier. Okay, so just as either reminder or introduction, if I have two functions and they have a Fourier series representation, then I can take their dot product. Okay, so here is a function f dot product with a function g. Now I've specified that my functions have a Fourier series representation. So this is to say that my function can be written as a sum of coefficients f hat L and these complex exponentials, so cosines and sines. Okay. And now I've got my same representation for my function g. Now recall that because I'm taking a dot product in a complex space, that means I need to switch the sign of this I here. And if this is complex, I need to switch the sign of the complex spot. Okay. So this is just because I'm taking a dot product of a complex number. So basically, because a dot product is linear, I take the sums outside the dot product, and then I get the sum of FL and GL, where I've taken the, where I've flipped the imaginary part, e to the ILX and e to the minus MX. Now, here we remember that these functions here, e to the ILX and e to the minus IMX, where the minus sign comes from the bar, these form an orthonormal basis. And so these are 0 unless L equals M, in which case they're 1. So that means that the double sum becomes a single sum, the sum of f hat L and g hat L with the bar on top. Okay, so that is the standard dot product of two functions which have a Fourier representation. Now I am going to define out of nowhere a new dot product. Okay, here is my new dot product. What is the difference? Well, the top is the same, but now I'm dividing by the Fourier series of my kernel. So why would I do that? The reason I would do that is because if I take the norm of f, which is a dot product of f with itself, if I do the square norm, then what this looks like, I've got the dot product of FL and f hat L divided by KL, which is basically the sum of the FL squareds divided by KL. So if I just had the standard norm, this denominator wouldn't be there. But I've added this K hat L to my denominator. And the effect of the K hat L is that it makes the norm of f a roughness penalized norm. All right. So remember what our K hat L looked like for this Gaussian-like kernel. The K hat Ls, which are on the bottom right figure here, decay like a Gaussian. Okay, they're decaying very, very quickly. Now that means that 1 divided by K hat L increases very, very quickly. So that means that if I want my norm to be finite, these f hat Ls had better decay fast. Otherwise, this sum is going to explode. Okay, So in other words, what it means is that it restricts the class of functions for which this norm is finite, because if my functions are not smooth enough, then this norm is going to blow up. And this is unlike the standard norm, which didn't have this k hat L in the denominator. So my norm, which I'm going to mandate, is an RKHS norm. I'm going to specify that this is the RKHS norm, is a roughness penalized norm. Another thing that arises is if I say that I want this norm to be small, if I force it to be small in my algorithm, that means I will get a smooth function. I'm forcing it to be small. I'm forcing these things here, these f hat Ls, to decay fast. Okay, so now we will have a poll. So earlier on, I defined a top hat function. Okay, and I defined a kernel, right? This kernel, which was the Jacobi theta kernel, which was a Gaussian-like kernel. Now let's say that this is my norm. Let's say that these k hat Ls come from my Jacobi theta kernel, from my Gaussian kernel. Let's say that these f hat Ls come from my top hat function. So my poll to the audience is going to be, is the top hat function in the RKHS? So let's first have everyone put their hand up if they think it is. And Mijun can count the number of people putting their hands up.
All right. 1, 2,
Only 1, 2,
okay, 3,
3.
5, 4, 5. Okay.
Okay, so we'll say 5. Okay. Now put up your hand if I don't know who you are, by the way. So like, there's no shame in putting your hand up. I don't have anyone to blame. Now put up your hand if you think it's not. And Mijun will count. And nobody keep their hand up because that's cheating.
Okay, they are still raising hands. It takes some time. 18,
Okay.
18 out of 86. Oh, 21.
18.
Yeah.
21. Okay. And I will say, put your hands up if you're looking at Twitter instead of listening. No. Okay. So basically, the majority is correct. And I'm going to explain now why the majority is correct. Okay. So let's go back to this function here. Let's go back to this Gaussian kernel. K hat L is decaying exponentially. Okay, it's decaying as e to the minus L squared. That's very, very fast decaying. Let's go now further back to the top hat function. These are the f hats for the top hat function. And these are decaying. Remember, the sine function never decays. The sine function just wiggles from -1 to 1. It continues to do that, right? This decays as 1 on L, right? So f hat L squared decays as 1 on L squared. F hat L decays as 1 on L squared. K hat L decays as e to the minus L squared. So now let's look at this sum here. Well, the numerator is decaying as 1 on L squared, but the 1 on K hat L is increasing as e to the L squared. So clearly this sum isn't converging because an exponential increase is increasing much, much, much faster than a polynomial decay. So the sum is going to diverge, and the top hat function is not smooth enough to be in the RKHS. So this is quite interesting. This function isn't smooth enough. I need smoother functions before I'm allowed to be in my RKHS. So, when I say that my RKHS enforces smoothness, it really does. And this norm being finite means that I'm only considering smooth functions. Okay, this is a technical point on the bottom of the slide, but I won't dwell on that. Okay, so now let's check that our famous reproducing property holds. Okay, now to do that, I'm going to use the dot product from a couple of slides ago. Okay, remember this is the dot product. F and G is the dot product of the Fourier coefficients that define F times the conjugate, so the complex flipped Fourier coefficients of the function G divided by the Fourier function coefficients of K. All right. Now I need the reproducing property, which is that I need to take the dot product of F with K. And for that, I need to get out F at Z. And I'm going to check that that holds when I use the dot product that I defined on the previous slide, this roughness penalized dot product. Now, I need to take the dot product of F and this function here. This function is going to be my G. So my g is going to be expressed as a function of x centered at z. So think of z as the point at which my kernel is centered, and x as the argument. So it's a function of x centered at z. That means my Fourier coefficients are going to be the Fourier coefficients of k times e to the minus ILZ. So this is something that you might want to sort of revisit tonight when you look over the slides, because it's something that confused me a bit when I was first learning it. Okay, so these are the Fourier coefficients that define our function, and x is the argument of our function. So we sort of think of this as being a function of x. Okay, let's put this function of x in here. So this is my g. And let's take this dot product now using the roughness penalized dot product that I defined a couple of slides ago. Okay, so dot product of f of k. Well, here is my Fourier coefficients of f. Here are my Fourier coefficients of z. Okay, where I've had to switch. Notice I've switched the sign here because of this bar. And k is real valued, so I didn't have to do anything to that. And now this k and this k cancels. And then I just get the Fourier representation of f, and I'm done. So my roughness penalized dot product satisfied the reproducing property. So, this is, I think, quite interesting. We've constructed our RKHS, we found what the features look like, and we verified that the reproducing property holds when we use this roughness penalized dot product. So this is what I meant when I said that the reproducing property is not trivial. You need this interesting dot product, and then you can show that the reproducing property holds with that dot product. Now your exercise tonight is to show that the same happens when I take the dot product of the kernel centered at y and the kernel centered at z. So this is something you can try tonight to convince yourself that even this second part of the reproducing property holds. And in fact, it's going to be a pretty simple exercise, because you're going to define your function g as we did here, which is a function centered at z. And I'm going to define a second function f, which is going to be my kernel centered at y. And when I take the dot product of that f and the g, I'm going to get my kernel of y minus z, using much the same algebra as I used before. Okay. Are there questions about that before I go on to my next slide?
Yes, we have one question.
Good.
Yes, so the question was about the top hat function again.
Mm-hmm.
So if I understood correctly, you said that the top hat function is not in the RKHS,
Mm-hmm.
but still, did I understand correctly that we can approximate it arbitrarily well if we consider more and more terms?
Right. Yeah.
But
So
this,
yep. Mm-hmm.
But this approximation, does it converge in some sense to the top hat function? And if so, the top hat is still not in the RKHS. Right.
So basically, so this sort of gets to the question of like, how rich is your RKHS? And so what's interesting is that the Gaussian kernel, for example, is a universal kernel. So that means that on compact domains, it can approximate any continuous function arbitrarily well in the infinity norm. Now, the top hat function is not a continuous function. It has discontinuities. So there is a second function, which is a Witch's hat function, which is like a triangle rather than a square. So this is a function I would expect to approximate arbitrarily well at any x using a Gaussian kernel.
I see.
Yeah. But it is, again, it's outside of the RKHS, because the Fourier coefficients of the Witch's hat also decay polynomially. They decay faster. It's a smoother function than the top hat, but still not fast enough for it to be in the RKHS. Yeah.
Thanks.
And in fact, that's a very good question, because it sort of speaks to a broader property of the RKHSs, which is that even though they can only contain the smooth functions, they can often approximate less smooth functions very well. And so that can actually be a useful property. And so this slide here, which I will just sort of warn everyone, this is the most mathematical slide in this entire course. So bear with me. This is to connect the reproducing property and the notation that I started this talk with the Fourier representation that I ended the talk with. So I'm just bringing everything together in one slide. And so this is in a way for future reference, but I'll walk through it anyway. So here is from the first half of the talk. I said f of x is this infinite sum of FL and phi Lx, okay? Now, because I'm now in the complex world, I've got a sum from minus infinity, and I've put the bar on the second term of my dot product because I need to do that for complex dot products. Okay, so this is my f dot and my phi of x, my function and my features of x. Now, in the Fourier land, we defined our dot product as this smoothness penalized dot product in terms of the Fourier coefficients of f, the Fourier coefficients of g, and the Fourier coefficients of k, right? So this is the second half of these lectures. And I've said that the dot product of f and k are the dot product of its Fourier coefficients. These coefficients here, which are the coefficients of a function centered at z, a kernel function centered at z, and this k hat L. Now I've done something a little bit unexpected here. Before you saw k hat L all on its own, but here I've done the square root of k hat L squared, which seems that I've just done something a little bit weird because the square root of k hat L squared is just k hat L. So why did I do that? I did that because I wanted to do pattern matching between this first line and this second line. And in particular, blue FL is the Fourier f hat L divided by square root of k hat L. And my feature of x is square root of k hat L times e to the minus I Lx. So basically, this first line and this second line are related by this third line. And this is, as it happens, rather trivial algebra. And as before, the norm of f I can write here, which shows why it's a roughness penalized norm, because I've got these Fourier coefficients squared divided by k hat L. Or I could write it just as I did before with my blue FL squared. So to my mind, this representation here is the more informative one because it tells me why it is that I'm getting a roughness penalty. It tells me that my Fourier series coefficients are being penalized in this way. But this is just to give coherent notation between the first and second half of the slides. So are there any questions about this slide? Okay, so that's just a nice summary slide. All right, so I've said that the RKHS norm is a roughness penalty, and I'm now going to illustrate this with a particular example. So this is your machine learning 101 example, which is ridge regression. But now that we've understood a little bit more about RKHS norms, we can understand exactly what ridge regression is doing. Okay, so here is kernel ridge regression. Kernel ridge regression, I'm looking for a function which is minimizing a function in an RKHS, which minimizes the squared error between my function and y. So remember, f and features of x, this dot product here is just my function evaluated at x, trying to make that close to y at these endpoints. But I've added here lambda times RKHS norm of f squared. And what we've just seen is that the RKHS norm of f is a roughness penalty. So if lambda gets big, I'm going to ensure that my function is smooth. I'm going to really penalize roughness. If lambda is small, then I don't care. My function can be wiggly. So here's an illustration. Lambda is 0.1 in this plot, and the function is a pretty good match to my data. Like I'm not fitting the noise, I'm just fitting the signal. Here lambda is 10 in the middle. Now when lambda is 10, I've required that my function be very smooth. I've really forced myself to penalize roughness here. And you can see that my function is almost flat. Now here I've got 10 to the minus 7 as my lambda. Here my function is pretty wiggly. And so here I just don't care. My function can be as wiggly as I like, and I'm not being penalized for it. And so that's the function I get out. And so you can see here that by adjusting this lambda, I'm able to adjust how smooth my function is. And so now we sort of understand well what ridge regression is doing. Okay, so that's the end of my introduction to kernels. Are there questions about that? Okay, good. So what I'm going to do now, yep. Is there a question? Excellent.
Wait, okay.
Yeah, sorry, it's me again. So I'm still a bit confused about this like smoothness thing, because the kernel you used had this nice property that actually the first function in our representation was very smooth, and then they got less smooth. But can you think of a kernel where basically, let's say, the first approximation is a step function or something which is really non-smooth, and then let's say higher order higher order basis functions become more smooth, where it's basically the other way around? Or is that something weird? Because to me, it's not so clear why the kernel, why the lower order approximations are smoother than the higher order approximations.
Right. Yeah, I mean, so I think for this, I think it's helpful to go even back a little further. Let's go back to this one. So as a general rule, this is a sort of general way to construct these kernels, where we use the eigenfunctions of our kernels with respect to some probability measure. So what you, in a sense, what you want in defining this is that the eigenfunction, like this expansion here, is a convergent sum that converges to this function here. Now, you can adjust your measure. So basically, when I was doing the Fourier expansion, the limits of my integral were minus pi pi, and this measure here was the flat measure. Okay, so that's how I got my Fourier representation. In that case, my eigenfunctions are just the Fourier basis. Now here, my limits are minus infinity, infinity. My p is a Gaussian, and I'm getting these Hermite polynomials. If I chose a different measure here, I would get different shapes here. No longer Hermite polynomials. I probably couldn't get them in closed form, but I would still get out this function. So in a sense, why I expect to get out smooth eigenfunctions is because I need something that is converging to a smooth function when I do integral over some measure here, where my measure has to have support over the whole space for this thing to be valid. In the specific case of the Fourier, I'm using a uniform measure. I'm using minus pi pi, so I know exactly what eigenfunctions I'll get out. They will be the Fourier eigenfunctions. If I'm using Gaussian, I'm going to also get this ordered set out. I don't believe that you are able to get out a sort of disordered set of eigenfunctions using this expansion here, because we know it has to converge to a smooth function, and we know that these eigenvalues have to decay. So in a sense, the intuition you should have in mind is that if you start with a very rough function, you're going to spend the rest of your infinite sum correcting for it. And I don't know, I cannot think of a p that would allow you to get such a disordered eigenfunction set out. It would be fun to try and figure one out, but my intuition is that you're not going to be able to.
Thank you. Maximilian, do you want to ask a question?
Yeah, maybe just one quick question. Can you go back to the ridge regression slide? Just to be clear on what the argument actually means, over the f. So is argument f, are we searching then for the coefficients, basically, that we define in f? Or
that's a very good question. So basically, in this case, I've been I haven't gone into the detail about ridge regression because I'm just giving, in a sense, a high-level view. So here I'm saying, find me a function in my RKHS that has a small reconstruction error and that is smooth. Now, your next question might be, well, but this is a function with infinitely many coefficients. That's a bit annoying. Can I write it as a sum of finitely many kernels? The answer is yes. So it turns out that I can express the function only in terms of kernels that are centered at these xi's, at these training points. And this is a consequence of something called the representative theorem, which is that, if my function is only a function of my loss, and I'm using a regularizer, like a smoothness penalty like this, then it must be that my function is a function only of kernels centered at these points. And so indeed, what you say is correct, that I'm only needing to find the coefficients that multiply my kernels at those points.
Okay, and is this like a gradient-based thing then, or is it like a constraint optimization problem kind of thing? Or
life is actually easy. You can write a single line and you have it in closed form. Yeah.
Okay, that's nice.
Yeah. Okay, are there other questions?
Oh, yes, there is one more question.
Mm-hmm. Oh, what is the question? I'm not hearing it.
Hugo, I just promoted you. Can you unmute?
Hi, can you hear me?
Yep.
Yeah, so the question was, so we've seen at some point during the slides that the coefficient of the function are linear combination of the features.
Mm-hmm.
And I thought that this may be quite a strong restriction about how this function might look like. Is it the case or not?
Yeah, no, that's absolutely right. So basically, we have restricted ourselves to functions that are linear combinations of the features. And so what that means is that the burden of finding good nonlinear functions becomes a burden of finding good features. So like the hard work that you need to do is to define feature dictionaries. And then, the function that you then get is just a linear function of those dictionaries. So, where you're, in a sense, being clever when you're using kernel methods is in engineering good dictionaries, which might be infinite, which have nice smoothness properties that sort of tell you that when I'm making a penalty like this, I'm going to get up, I'm going to get a nice function out.
Like it's not only the functions that are linear in the features, it's also that the coefficient in this linear in this linear function are also linear function of the features, or did I miss something?
Right. So it is right. So the second point I think was the reproducing property, right? That we're going to hope that the functions that we get out are going to be sums of kernels. So in a sense, like, we have a sum of infinitely many features, but any practical algorithm is going to require us to express the solution as a sum of kernels. And so indeed, what we're going to need is something like a representative theorem. So we're going to say that, even though we're using infinitely many features, we only need to express those features as weighted sums of features of data points that we've observed. And if so, then we have the power of these infinite feature dictionaries. But if not, we don't. Yeah.
Last question. Like this thing about the smoothness, about how you control the smoothness and stuff. It's very linked to how you define your kernel, isn't it? Like because the kernel you define, the Gaussian kernel is like you can really control the smoothness, and it's by itself a smooth kernel. But I think I could come with a non-smooth kernel at all, which will completely break this smoothness interpretability.
So basically, like if your kernel has a Fourier transform, then, or more generally, if you have this sort of eigen expansion, you will be able to define feature spaces. So in a sense, I have here like this k hat, et cetera, and this arises because I have a Fourier transform. So, if let's say that I have a less smooth kernel, like, and I can define kernels with a much slower decaying spectrum, which will give me much less smooth functions. Nonetheless, as long as I have this Fourier transform well defined, which is to say that the k's decay fast enough that the sum converges, then I'm going to be able to write this smoothness penalizing dot product. So let's say now that I have a rough function like a Laplace kernel, which has a polynomially decaying k. That means that I can have a lot rougher functions and still be in my RKHS. And maybe that's what I want. Like if I'm trying to fit a function which is less smooth, maybe that's actually a good thing. And in fact, sometimes it is. Like sometimes that will be the better kernel for your problem.
I see. Thanks.
Yeah, but you like my argument is sort of relying on the fact that this sum here is converging, and so if it didn't converge, like what if k was 1 everywhere? Well, then you're screwed, right? Like this, that's not a. Then you're in the realm of distribution theory instead. Yeah.
Okay, we have one more question from Matthew.
Yep.
Hello. Yes, so I did DSP. Maybe I studied DSP maybe like going on 10 years ago now. And it's nice to see like Fourier popping up. And I was wondering if there are any nice little other gems that sort of like you've noticed that are similar between sort of Fourier, Fourier analysis, spectral analysis, and kernels that you're particularly like fond of, I guess.
Yeah. So I think there have been some interesting kernels developed for audio, which have been sort of like trying to extract particular spectral features. And so these are interesting, like you're defining a sort of domain adapted feature space from the spectrogram of audio signals. And that's been quite fun. So I think this is one area. I mean, that's the one that sort of comes to mind immediately. And in fact, there was, as an example, we did in one of our experiments, we were sort of looking at differences in distribution over frequency modulated signals from different soundtracks, and which we did basically as a sort of stunt to prove that we could do it. And this sort of required us to adapt our kernels to basically, demodulating and recovering signals from amplitude modulation, and that was just something we played around with a little. Yeah.
Thank you. Any more questions? Oh, there is one question from the chat.
Oh.
The RKHS norm correspond to a smoothness penalty for all kernel choices. I thought k hat depends on the choice of kernel.
Right. Yeah. So k hat absolutely depends on the choice of kernel. So this is what we have here. So in this little example, we have k hat being the Fourier series coefficients of k. If I used, rather than a Jacobi theta kernel, so Gaussian kernel, some other kernel like a periodic Laplace kernel or periodic inverse multi-quadrate kernel, I would get a different speed of decay of k hat L. So here k hat L is decaying extremely fast, e to the minus L squared. If I used a different kernel, I would have different decay properties. That would mean that I would still have a roughness penalizing dot product, but maybe I would penalize roughness less, or maybe I'd penalize it more. So the amount by which I'm forcing my functions to be smooth or not smooth will absolutely depend on the kernel that I choose. And so I should then choose a kernel with my problem in mind. If I think I'm going to get very smooth functions, I should choose my kernel accordingly. If I think I should get rough functions, I should choose my kernel accordingly.
Thank you.
So I have can I ask a quick question?
Of course.
So in the kernel regression slide, so the way you write it, basically when we minimize the objective with respect to f, so basically this amount to optimizing the linear coefficient, basically the coefficient in f.
Right.
And basically here you fix the feature map data. I'm curious, how is it related to, let's say, deep learning, basically here?
Right. Yep. So, I mean, in the case of deep learning, one would have feature dictionaries here that one would then learn, right? So in a sense, like this thing here would be your top layer. And then you would learn these features, which would be like finitely many by backprop. And this might be the deep neural net. What we're doing here is we're saying, well, I've got a fixed but infinite feature dictionary. And I'm going to express my solution not as basically a sum of these finite but deep features, but as a sum of kernels at xi. So if, for example, let's say that I had a function which was more smooth in some parts of my space and less smooth in other parts of my space, then it may then make much more sense to use a deep neural net here, because a kernel method is basically, if I'm using a translation invariant kernel, that amounts to saying that my function is equally smooth everywhere.
But is there a way to modify your RKHS in such a way that you can allow the different degree of smoothness depending on where you're in space?
Indeed, there is. So there's a couple of ways one could do that. One is to define explicitly a non-stationary kernel by basically having a location-dependent bandwidth. But another way, which is the way that I'll talk about in the second part of this course, is to define a kernel on a deep network of the data and to train it. And then you get a kernel that's actually changing shape around the space. And it sort of is a combination, like it's a sort of, a pre-processing deep layer, and then some smooth functions of those deep features. And so you're, in a way, getting a hybrid model, which is using both. And this hybrid model is something that we're using in some settings.
I see. Thank you.
Any more questions? Okay, no. Well, we're on time.
In fact, we are on time. Yeah, so good. So I guess, so come back tomorrow and there will be some other fun material. Yeah. But today was the theory talk, as I emphasized. So now that we have this understanding of where these feature spaces come from, tomorrow we're going to be using these in applications. But because we have this understanding, the applications will become a lot sort of clearer. Yeah.
All right, thank you. So we will see Arthur again in 30 minutes in the roundtable session. Okay, and see you later. Thank you. Bye-bye.
Thank you, Arthur. Bye.
Thank you.